Our planet is a living, breathing system. It receives a constant stream of energy from the sun. This energy warms the land, the oceans, and the air. But for life to exist, this warmth must be balanced. The Earth cannot simply keep getting hotter and hotter. It must have a way to release this heat back into the cold emptiness of space. This process is like a great, slow sigh. It is a fundamental rhythm that keeps our world in a delicate equilibrium. Without this cooling, our home would become a barren, scorched rock, unable to support the wonderful diversity of life we see all around us. The main way our planet cools is by sending out energy. This energy is not visible light like the sunshine we receive. Instead, it is a type of invisible light called infrared radiation. Everything with warmth gives off this radiation, including you and me. The Earth's surface, warmed by the sun, radiates this heat upwards. Some of it gets trapped by our atmosphere, a process known as the greenhouse effect, which is vital for keeping our planet warm enough for life. But a significant amount must escape. It travels through the air and out into space, carrying heat away from our world forever. Clouds play a fascinating and complex role in this great balancing act. They are like a two-sided coin for temperature. On one side, they act as a bright white shield. They reflect incoming sunlight back into space before it can even reach the ground. This has a powerful cooling effect, much like a parasol on a sunny day. High, thin cirrus clouds, however, can act differently. They are less effective at blocking sunlight, but are quite good at trapping the heat that is trying to escape from the surface below. So, the type of cloud, its height and its thickness all determine whether it cools or warms the planet at any given moment. This constant exchange of energy, the incoming warmth from the sun and the outgoing sigh of heat from the Earth, is called the energy balance. It is perhaps the single most important system for regulating our climate. When more energy comes in than goes out, the planet warms. When more energy goes out than comes in, the planet cools. For millennia, this balance has shifted back and forth, creating periods of warmth and periods of ice. Understanding what tips this balance towards cooling is crucial to understanding the story of our planet's past, and indeed its future. Nature itself has powerful ways to cool the planet. Sometimes this cooling comes from deep within the Earth. A large volcanic eruption is a dramatic and forceful event. It can send a huge cloud of ash and gas high into the atmosphere. One of these gases, sulfur dioxide, mixes with water to form tiny droplets called sulfate aerosols. These particles are incredibly reflective. They spread around the globe like a dusty veil, scattering sunlight back into space. After the eruption of Mount Tambora in 1815, the world experienced the year without a summer, a stark reminder of how volcanoes can temporarily turn down the planet's thermostat. The sun, our ultimate source of heat, is not perfectly constant. Its energy output changes in regular cycles, typically lasting about 11 years. During periods of lower solar activity, the sun sends slightly less energy towards us. One famous example is the Maunder Minimum, a period of very few sunspots from 1645 to 1715. This solar quiet spell coincided with the middle of the Little Ice Age, a time when glaciers advanced in Europe and winters were particularly harsh. While not the only cause, these subtle changes in the sun's brightness can contribute to global cooling trends over decades. Our vast oceans are the planet's great heat regulators. They move enormous amounts of warmth around the globe through currents. But sometimes, natural patterns in the ocean can lead to cooling. The La Nina event is a wonderful example. During a La Nina, cooler waters from the deep Pacific Ocean rise to the surface. This large patch of cold water absorbs heat from the atmosphere above it, leading to a temporary drop in average global temperatures. These events show how the ocean's internal rhythms can have a significant and immediate impact on our global climate, creating cooler and wetter or drier conditions in different parts of the world. Over much longer timescales, spanning thousands of years, the Earth's very orbit around the Sun changes. These are known as the Milankovitch cycles. The shape of our orbit shifts from more circular to more oval. The tilt of our planet's axis wobbles. These are slow, predictable cosmic rhythms. They alter how much sunlight different parts of the Earth receive and at what time of year. These cycles are the main drivers behind the Great Ice Ages. When they align to reduce the amount of summer sunlight in the northern hemisphere, ice sheets can begin to grow, slowly plunging the planet into a long period of profound cold. While much of our modern focus is on human-caused warming, it is true that human activities can also have a cooling effect. One of the most significant, though unintentional ways we have cooled the planet is through air pollution. The burning of fossil fuels, especially coal, releases not just greenhouse gases, but also sulfate aerosols, the very same tiny particles that volcanoes produce. These shiny pollutants create a haze that reflects sunlight back to space. This phenomenon, sometimes called global dimming, has masked some of the warming that would have otherwise occurred. It is a strange paradox. The same industrial activity that warms the planet also produces pollution that cools it. We've also changed the land itself, and this can alter local and even regional temperatures. When a dark forest is cleared and replaced with lighter-colored cropland, the new surface reflects more sunlight. This is known as a change in albedo, or reflectivity. A more reflective surface absorbs less of the sun's energy, which leads to a localized cooling effect. Building large cities creates a heat island effect, but transforming vast landscapes for agriculture can, in some cases, slightly increase the amount of solar energy reflected away from the Earth, contributing a small but measurable cooling influence over large areas. The cooling from aerosols, however, comes with a serious trade-off. These same pollutants are responsible for acid rain, which can damage forests and aquatic life. They also cause serious human health problems, contributing to respiratory illnesses. As many nations have worked to clean up their air by installing scrubbers in power plants and improving fuel standards, this aerosol pollution has decreased. This is wonderful news for public health and the environment, but it means that the cooling effect of these particles is also reduced, unmasking the warming from greenhouse gases that was previously hidden. So, the human impact on the climate is not a simple one-way street. We are conducting a vast, unplanned experiment with our planet's atmosphere and land. While the dominant and long-term effect of our activities is overwhelmingly one of warming due to greenhouse gases, we have also simultaneously introduced cooling factors. Understanding this complex push and pull is essential. It shows that actions taken for one reason, like reducing air pollution, can have unexpected consequences for the global temperature balance, highlighting the intricate connections within our Earth systems. Looking back in time, we can see clear evidence of when the Earth was much cooler. The Little Ice Age, from roughly the 14th to the 19th century, was a period of regional cooling. It was likely caused by a combination of factors, including lower solar activity and a series of large volcanic eruptions. This period saw London's River Thames freeze over and Norse colonies in Greenland collapse. Going back even further to the end of the last Great Ice Age, a sudden and dramatic cold snap called the Younger Dryas occurred. It is thought to have been triggered by a massive flood of fresh water from a melting North American ice sheet, which disrupted ocean currents and plunged the Northern Hemisphere back into icy conditions for over 1,000 years. So, is the Earth cooling now? The answer is a clear no. Despite the short-term cooling effects that still occur, the planet is warming at an unprecedented rate. The immense quantity of greenhouse gases we have added to the atmosphere has overwhelmed the natural and human-made cooling factors. The planet's energy balance is now firmly tipped towards warming. Natural cycles like La Niña events and occasional volcanic eruptions can still cause temporary dips in the year-to-year temperature rise. For instance, the eruption of Mount Pinatubo in 1991 cooled the planet by about half a degree Celsius for over a year. These short-term cooling factors remain a vital part of our climate system. A major volcanic eruption tomorrow could briefly pause global warming, but it would not reverse it. The underlying warming trend, driven by greenhouse gases that stay in the atmosphere for centuries, would continue as soon as the volcanic dust settled. The fundamental physics is clear. We are trapping more heat than is escaping. Until that energy balance is restored, the long-term trend will be one of increasing warmth, punctuated by fleeting moments of natural cooling. This understanding has led some to consider whether we could intentionally cool the planet. This idea, known as geoengineering, involves proposals like deliberately spraying aerosols into the stratosphere to mimic a volcanic eruption. These concepts are highly controversial and carry enormous risks. They do not address the root cause of warming and could have unforeseen and potentially disastrous side effects on weather patterns and ecosystems. Our planet's cooling systems are complex and powerful, but they are now being overcome. The challenge remains not to invent artificial ways to cool the Earth, but to restore the natural balance we have so profoundly disturbed.